Okay, so let us continue with this exercise which we are calling a discuss exercise. It helps to give some special names to these exercises that we are in fact making because, for example, you can see here, discuss the group on page 69 of the text and verify the result of the previous derive the result of the previous verify exercise. So the previous verify exercise is the one that we saw in the previous video, where we constructed that 21 order non-abelian group, and this one is the general version of that that we have already come across in the text, where we consider a general group G and an automorphism T of G that is not an inner automorphism. Using these two things, the author says that we can create a non-abelian group which is denoted like this, and in this group G sits inside in some sense G sits inside this non-abelian group, and when you consider G as a subgroup of this group, it is normal. And if one forms the quotient of this group by G, because that can be formed, G is a normal subgroup, then that quotient is isomorphic to the cyclic subgroup generated by T in the automorphism group. Oh, and one more thing is that T, besides being not an inner automorphism of G, also has finite order, some order R. Okay, so we are first of all going to show these things, and then we will have to show that the group we constructed in the previous exercise, that is a special case of this one. So in that sense, this is a generalization of that. So let us see how to proceed. We begin like this. We have first of all, we say what this set is. It consists of formal symbols like this, where I varies from 0 to R, where R is the order of T as an element in the automorphism group of G. We are not mentioning that separately. Oh, but if R is the order of T, there is no need to go up to R. It's enough if we consider the integers up to R minus 1, because we will see, because why that is not necessary. And G is an element of G. Okay. Now on this set, and this is the criterion for two such symbols to be equal. I1 G1 equal to x to the power I2 G2, where it's understood that these are symbols coming from this set, and as such G1 and G2 are elements of our group G, and I1 and I2 are integers in this range. If and only if I1 is congruent to I2 modulo R, and G1 is just plainly equal to G2. If the group elements are equal and these exponents, or we should not call them exponents because these are formal symbols, not to be interpreted as x to the power I1, just superscript of x. So these integers are congruent to each other modulo r. Okay. Okay, now we define the binary operation that we want in this set to make it a group. So for H belonging to G comma T, we define the operation like this. Equal to which I should write carefully, I plus j. But just like the previous verify exercise, here also the plus is not ordinary addition but a special type of addition which gives us the remainder when the ordinary sum I plus j is divided by r. And along with that, this thing G P J H. Let us first make sense of this. These are two symbols coming from this set, fine. And there, when we operate them, this is the result. Now, I and j, each one of them is an integer lying between 0 and r minus 1. That is also, there is no problem with that. So I plus j is some integer lying between, because we are adding, and 2r minus 2, r minus 1 plus r minus 1. After all, it's an integer. Now when we divide this ordinary sum by r, the remainder that we get will obviously be one of these integers, because when we divide by r, these are the possible remainders. So that means the number that appears above x is one of these. Okay, so there is no problem with this number. Above x we have the kind of number that we want here, but then that is accompanied by this. Now what is this? Here note that this is the jth power of t. What is t? T is our automorphism of group that is given to us. Now what is the meaning of the jth power of t? Its meaning is just simply t is an element in the automorphism group of G. Now as an element of a group, its jth power can be calculated, and t to the power j will again be an automorphism of G that has been applied on the group element G. So this G t to the power j itself is a group element in G, and H is of course again a group element. We are taking their product in the group. So the part that we see within square brackets, that is again an element in G. So this final thing that we are getting is again a symbol in this set. Okay, so that means whatever we have done here, it ultimately again gives us a symbol like this. Fine, but you know that this is not enough to make this operation well defined. Something else is also needed. Namely, when you operate equal symbols, then you should get equal results. So we are now going to show that that is the case. We can just simply write, although I haven't, but before we do anything else, we should say what this plus r means, where I plus rj denotes the remainder obtained on division of I plus j by r. Okay, now we can write, note that this belongs to our set of formal symbols. And you can see that it's very easy to remember this also. It's not as messy as the previous special case of 21 order non-abelian group. I and j are of course going to be added using this special addition. But then what you do, g, x and h, you just replace x with t, g, t, h. T to the power j comes in place of x to the power j, and you meaningfully arrange the things and you get the operation. Okay, so now we come to the question of well-defined, this operation being well-defined. For that we have just simply written, it's easy to show. Okay, based on the experience that one has in solving the previous verify exercise, one can write, if one wants, here that it's easy to show that this operation is well defined, but instead we are going to do it. Let x to the power I, x I1 g1, x I2 g2, x j1 h1, x j2 h2 belong to our set such that this is equal to x I2 g2 and x j1 h1 is equal to x j2 h2. Okay, now using our criterion for equality of two such symbols, we then have I1 congruent to I2 mod r, g1 equal to g2, then j1 congruent to j2 mod r, and h1 equal to h2. Okay, so that means g1 is equal to g2 and h1 is equal to h2. This implies I1 plus J1 is congruent to I2 plus J2 mod R. We have added these two congruences, and hence I1 plus RJ1 congruent to I1 plus J1. We have already seen in the previous verify exercise solution why these two things are congruent but to each other modulo R. And this we have just now shown is congruent to I2 plus J2, and this in turn is congruent to I2 plus R J2 mod R. Okay. Also, since G1 is equal to G2, so we will have this. Oh, but there is one more thing that should have been there is one issue. It's not an issue actually, but it should be made clear. Also, G1 t to the power J1 H1, the other half of the, one half of course will involve these numbers above x in our final symbol. The other half is the group half, that is the half that will belong to capital G. Okay, now before we start this calculation, I think it's better to say why t to the power J1 is equal to t to the power J2. Let's first take care of that. Since J1 is congruent to J2 mod R, J1 is equal to KR plus J2 for some integer k, because then J1 minus J2 is divisible by R, and that's why we have this congruence. And conversely, for some integer k. Hence, now we can start that calculation. G1 t to the power J1 H1. In place of G1 we can just directly write G2 because they are equal. Now in place of J1 we are going to write this KR plus J2, and in place of H1 we will write H2 using this. Okay, now G2, note that this integral power of T is an integral power of T in the automorphism group of G. So using the rules of exponents, you can write that integral power like this. I mean, this is the full function that is being applied on G2, and with that we of course also have H2. Now this is where that part of the hypothesis comes into play, which says that T has order R. As an element of the automorphism group of G, the automorphism T has order R. So this becomes the identity automorphism and it vanishes, and we are left with G2 T to the power J2 H2. So these two things are equal, and these two remainders are congruent to each other modulo R. Thus we have I1 G1 J1 H1 equal to, by the definition of our binary operation, this is I1 plus R J1, and with that G1 T to the power J1 H1, but this is equal to I2 plus R J2 G2 T to the power J2 H2. And the reason for these two symbols to be equal is that these numbers above x are congruent to each other modulo R, and these two things are equal. I mean, this one and this one in the group G, and this is equal to x to the power I2 G2 and xj2 H2. So the operation defined above is well defined. So it's a well defined binary operation on this set G comma T. Okay, now the next step of course is to show that this operation is associative. So we now turn to that, but let me just refill before that. I think I'm losing ink. Okay, next let us consider three elements, three symbols in our set G, H and U. Oh, we have chosen K. That K may get confused with this k. Okay, let us take, since we have already used it, let us write L in place of k. Then this will be LR L, that's it. Its role is only till this. Okay, so this one, and then J H K U, this be 3 symbols in our set. Now we are going to operate on them. XIG XJH XKE. Will it be better if I write it like this, like an equation array? Okay, so first the inner one, I plus RJ G T to the power J H. Now the outer one. Okay, so what is it that we have to do here? First, let us see the numbers above x. I plus j plus r k, and then first we have this group element. This is a group element. On this group element we are applying the automorphism t to the power k, and with that it's raining. With that we have the other element u outside, and this is one element. How should I write? There's so many brackets I have to write, but there is no other choice than writing these things. Okay, so on this group element we have applied the automorphism t to the power k. Then again we get a group element. That group element, we are taking the product of that group element and u in the group capital G. Okay, now this is a place where you probably can guess what we are going to write next. We will just simply write this, exploiting the fact that this special addition is associative. Actually it is associative, but we don't really need to show that these two integers are equal. We just need to show that they are congruent to each other modulo r, which we will show after we finish this calculation, and this we have done before also. Now here, okay, now let us come to one point which we mentioned in the previous video, namely, why do we need an automorphism? in all these things. I mean, what is the role of the automorphism in doing all these things? Do we really need a function which is an automorphism? We need a homomorphism. That will become clear now. You see, T is a homomorphism. It's an automorphism means after all it's a homomorphism. Let's forget for a moment that it's bijective as a mapping. It's a homomorphism on G. So this integral power is also a homomorphism on G. And these are two group elements. One of them is G T to the power J and the other one is H. So using the fact that T to the power K is a homomorphism, we can write this times H T to the power K. Had T to the power K not been a homomorphism, we would have stuck here itself, okay, after which we cannot do anything. Now note that here we have composition of mappings. So that means this is this product is the product in our automorphism group, where the binary operation is composition of automorphisms. Okay, so this is one group element H T to the power K. This is another group element, and outside we have U also. Okay, now this of course is a product of two integral powers of T. So in the automorphism group of G, these are integral powers, so we can use the rules of exponents here and write J plus K H T to the power K U. Okay, now we are going to write something else which we will justify afterwards. We are going to keep this same, almost like the previous one. The only change is in place of J plus K, we are going to write J plus RK. That's special plus. Can we do that? Yes, we can do that. Let's just assume for a moment that we can do that. We will say afterwards how. Now in place of this final element, if we write this, will it be okay? J plus K just apply the definition of our binary operation. Above x we definitely will have this, because this is the number above x here in the second symbol, and here above x we have I. So I plus R, that number. And then what about the group part? In the group part we will have G, on G we will apply t to the power this that we have done. Along with that we have whatever we have here, the remaining part, that also we have. And one more thing you can see is that there is one intermediate step. The intermediate step is this: if one goes backwards, one will get this. From here one will write this, and on G we are applying, so we get one element, you have the product of that and this. Whereas here we have almost what we have here, but in this part we don't quite have what we have here. The only difference is that with this product we have multiplied u here, whereas here we have a slightly different way of calculating the product. But this element and this element in G are equal because the binary operation in G is associative. So we are not writing that intermediate step. Okay, and we just simply write this equal to this directly. Now here you can see this is equal to H K U. Let's see if we really get that. X to the power j plus r k, fine. Then on H we have to apply t to the power k. Yes, we have that. And along with that we have u. Okay, so this shows that the operation we have defined is associative, provided we justify these things. One of the two things we have to justify. One of them is of course this one. These two numbers that appear above x are congruent to each other modulo r. And the other thing is this. Okay, so let's do them one by one. To justify the above calculation, we observe the following. Note that this we almost know what is to be done. You just one by one you replace the special classes by ordinary additions, and which itself is justified. We have already seen that previously. So this is congruent to this modulo r, and this itself is congruent to this, which in turn is congruent to this, because ordinary addition of integers is associative. R plus k, which is congruent to K mod R. Oh, and then that J plus K, that thing. Also, since J plus K is congruent to J plus RK mod R. In fact, this is what we are using here in these calculations. We have J plus K equal to, what should we take? The power is gone. Anyway, so J plus K equal to L we took previously. Let's take M. I don't think we have used M anywhere. No. MR plus this remainder. For some integer M. Hence, here also now you know, you can, I hope you can see what we are going to do. MR plus K, this is equal to, now we are going to use the rules of exponent. To write this as t to the power r or to the power m times t to the power j plus r k. Again, since r is the order of t, so that part vanishes and we are left with this. So we have justified our that previous calculation also. Therefore, the operation we defined on our set of symbols is associative. What else do we need? Existence of identity and existence of inverse for each element. Identity is very easy to guess, which is just this. One can verify that the element x to the power 0 times e in g comma t acts as an identity. Also, for any element this belonging to g comma t. Let me before we write something else, let me again stress the fact that in the calculation where we showed that our operation is associative, the fact that T is an automorphism, or rather more specifically that T is a homomorphism, plays a crucial role, because otherwise we cannot complete the calculation and we will not get what we got here. Okay, so for any such element, one can verify that its inverse exists and is this if I is equal to 0 and x to the power r minus I times g t to the power r minus y inverse if I is not equal to 0. I leave the verifications of these things to you guys. This of course is going to be extremely trivial. Let us just see at least one of the parts. Say you have this arbitrary element, you take the product of that element and this one. Okay, so according to our definition of our binary operation, I plus r0 g t to the power 0 e. So this is the remainder when we divide I plus 0 by r, that is when we divide I by r. Now since I is itself less than r and non-negative, so the remainder when you divide I by r is I itself. So this is I. And what is t to the power 0? T is an element in the automorphism group of G. So its 0th power is the identity element in that automorphism group by definition of integral powers, which is the identity automorphism. So applying that on G, we get G itself and we have E here. So we get the element back. There is another calculation where you switch the positions of the elements. There also you will see that you get the element back, which proves that this acts as an identity. Similarly, in these two cases, you can verify that the mentioned elements act as inverses. I mean, in each case, of course, it's going to be different. You have to take the cases and then verify that if you, for example, I is equal to 0, then if you take the product of x to the power 0 g and x to the power 0 g inverse, you are going to get this identity element. And also if you change the order, and in this case also, this is somewhat more complicated because of the presence of non-zero I. Here the inverse appears like this, x r minus I, and then on G you apply t to the power r minus I, so you get a group element, you take the inverse of that element, then this turns out to be the inverse of x to the power xig for non-zero I. Okay, so this part I leave to you. So provided you show these things, we can now say that our system is a group under the operation we have defined. Thus, this is a group. Fine. Okay, now just like the previous exercise, Previous, if you want, you can mention also previous verify exercise. Okay, now having obtained a group structure on this set, we can define X separately, and that X is going to be just this X1E. So we can define X like this, and we can define G also. For any group element G belonging to G. So you can see that okay. The way I have written here this thing, it may be somewhat confusing because G is already given to us. G is an element of our group capital G. Then what is the meaning of again defining G to be? Now it's somewhat confusing to say that we are defining G. Instead, what we are actually going to do is we are going to define a map between the elements of G and some special elements of this large group. Okay. Now only I am seeing this subtle confusion. And let's just continue from here. Define this and verify the relation. This relation X inverse GIX equal to GIT, where G means this. X has this meaning, X is this precise symbol in our set, in our group, and G is this symbol. Okay, with that, if you perform this calculation, then it will become the T image of G to the power I. And in this regard, what is given in the text is wrong. The relation wrong means it's a printing mistake, I think. In the text, it's given that the relation is this equal to gt to the power I. The meaning of gt to the power I and g to the power it are entirely different, and the fact that it is wrong is also going to be shown by us. In the text is wrong. for if we choose the element choose an element G not equal to E in G, then the proposed relation proposed in the text gives, if one considers the case I equal to 0, this E equal to x inverse Ex. You see, now it makes, this element makes sense. This E is the identity in our group that we have constructed just now. X is this symbol in the group. E is again an identity and X is just that. So this equation makes sense and it's an equation in this group. And now when we write, in place of E, when we write G to the power 0, you should interpret this G as not just simply the element G of the group capital G, but this element, this symbol in the other group that we have constructed. And this, according to the proposed relation, should be equal to G t to the power 0, because that's what the text is saying. However, since t to the power 0 is the identity mapping, this will be equal to G. So we get a contradiction because according to our choice, G is not equal to E. So whatever is given in the text is actually wrong. Okay. So fine. We have got our group and one can verify this relation. Verification of this relation is left to you. And now we need to show that our group is non-abelian. Let us now show that this is non-abelian. Okay, for non-abelianness we will do this. Fix an element H belonging to G. Okay, now this is the place where we use the hypothesis that our automorphism, we have already used one part of the hypothesis about T, namely that it's an automorphism and it has order R, which is a positive integer. Now we use the other part which says that T is not an inner automorphism. Okay, since T is not an inner automorphism, T cannot be equal to TH. Okay, T is not equal to that type of mapping. I mean, T is not equal to any of that type of mapping. In particular, for our chosen element H, T is not equal to TH. Now, what is the consequence of this? Thus, there exists an element G belonging to G such that GT is not equal to GTH. Now we know how to calculate GTH. GTH is H inverse GH because TH is an inner automorphism. Hence, now GT is not equal to H inverse GH. Hence, GTH, is it GTH? No, it is GTH inverse. So GTH inverse is not equal to H inverse G. That we get by looking at the first and last term of this inequalities, non-equality. Okay. This implies now what this in turn implies? This implies x naught G x1 H inverse. If one calculates this product in our constructed group, then we get 0 plus R1 G T to the power 1 H inverse. This will be x1 GT H inverse. Okay, and this is not equal to x1 H inverse G. Why? Because although here we have 1 equal to 1, but these two group elements in the group capital G are not equal. So the corresponding symbols are not equal in our constructed group. And this thing turns out to be x1. Now in place of H inverse we can write H inverse T to the power 0 because T to the power 0 is the identity map. And this, if you see, is equal to if one wants, one can also in place of 1 write this 1 plus R0 because that is going to be 1. So this is equal to x1 H inverse x0 G. Do we get this when we apply the binary operation 1 plus R0, then on H inverse we apply T to the power 0 and G? Yes. So this times this is not equal to this times this. So that's why the operation is not commutative and consequently the group is non-abelian. Hence, this is non-abelian. Observe that this is true even when G is abelian. That is the nice thing about this construction. Even when our original group is abelian, we are constructing a non-abelian group. Okay, now we are going to embed G inside this larger group so that the other parts can be shown. Okay, now define a map psi from G to this group by this formula. G psi is defined to be x0 G. Now there is no question that this map is well defined, because first of all the symbol that we are getting as output is an element here in the second set, and for a given G this symbol is unique. Clearly this is well defined. Now next we show that it's a homomorphism. For G and H belonging to G, we have GH psi equal to x naught GH. This, if you look carefully, it can be written as 0 plus R0 G t to the power 0 H, and this is equal to x0 G x0 H. 0 plus 0 using that special plus G t to the power 0 H. Now this is nothing but G psi, and the other one is H psi. Thus this is a homomorphism. Now for an embedding, this homomorphism should be shown to be an isomorphism, because then only G will be isomorphic to a subgroup of this, and in that sense G will can be made to sit inside this group as a subgroup, and then again we have to show that that subgroup is normal. Okay, so now we come to the question of showing that this is an isomorphism, that is psi is 1 to 1. So for that we show that the kernel of psi consists of only the identity element. Let G belong to K psi, which from the notation we have already come across this notation. This represents the kernel of the homomorphism psi. Then when we apply psi on G, we should get the identity element here. The identity element in this group is this. That should be equal to the psi image of this, which is equal to this. So from the definition of equality of two such symbols, we have, which implies that G should be equal to identity. Thus K psi consists of only the identity, and so psi is 1 to 1. It's injective. Hence G is isomorphic to the subgroup G psi, which is just the image of G under psi of this. Okay. Now, instead of directly showing that G or rather this subgroup is normal here, we are going to take one step more, and we at once consider the map. Which map should I consider? Let us consider phi from our constructed group to the cyclic subgroup generated by T. And how are we defining this map? For this map, we will have to say what the image, phi image of this element is, and that is defined to be equal to t to the power I. And we also mentioned this is the cyclic subgroup of the automorphism group of G generated by T. And because T has order R, this second group is a group whose order is R. Is this map well defined? For x to the power ig and x to the power jh belonging to this, or let's write like this, let this be two elements in our domain group such that they are equal. Then I is congruent to J mod R and G is equal to H. Although we have seen this two more times, but again let's just go through the detail. Since I is congruent to J mod R, I is equal to, or okay, yeah, we can write like this, I is equal to alpha R plus J for some integer alpha. Now the phi image of this, our aim here is to show that the phi image of this is equal to the phi image of that, because then only phi can be called well defined. Phi image of this by the definition of phi is t to the power I. Now in place of I we write alpha r plus j. Using the rules of exponent, we have this, which owing to the fact that r is the order of t gives us this, which is nothing but the phi image of this, the other element, which is actually just that element itself, another representation of that element. Thus phi is well defined. Okay. Now for let's take something else. Okay, we can take like this g1 and x to the power xi to g2 belonging to this we have. Now next we want to show that our map phi is a homomorphism. Oh, I think it's better to do the calculation here so that it's prominent. The good thing about this calculation, this one, is that we don't have to care about what is going on in the group G. We only care about what T is doing. I think it's better to, at this point, we have seen it enough number of times. In place of this, we can write this. And that is because these two integers are congruent to each other modulo r, and capital T has order r, that's why. Now using the rules of exponent in the automorphism group of G, this calculation is justified. This is G1 phi and the other thing is G2 phi. Hence phi is a homomorphism. Now note that phi is onto also. For any integer I lying between 0 and r minus 1, note that we have this element x to the power I e belonging to our domain group such that its phi image is t to the power I, and t to the power I is any arbitrary element in the second group, the cyclic group generated by t. So any such element appears as the output of some input under phi. So phi is onto, thus phi is onto. Okay, now we are next focused on finding out the kernel of phi. Next, let this be any element in the kernel of phi. Then we should get the identity element, which is the identity automorphism, because phi maps this group into this cyclic group, so where the identity is the identity automorphism. This should be the output of this input under phi, which according to the definition of phi is t to the power I. Okay. So t to the power I is equal to phi. This means, am I getting it right? T to the power I is equal to phi. Let me just see the hint. T to the power I is equal to t to the power I is equal to capital I, but of course okay. Now note that because our I lies between 0 and r, I mean not this particular I, but the I we have chosen here, that also lies between 0 and r, because we are after all choosing this symbol from the kernel of phi means what? After all, we are choosing it from here because the kernel of phi by definition is going to be a subgroup of this. So I satisfies these inequalities. Now look at this equation. T to the power I is identity. So from a previous result which we have used many times by now, the order of t divides I and the order of t is r. So we write that. This implies r equal to order of t divides I, since I is an integer satisfying these inequalities, we must have I equal to 0. Okay, so I should be equal to 0. Hence xig, which is equal to x0g, belongs to Do you see what this is? This is an element in G psi, that previous map psi, which is an embedding that embeds G inside this group. Thus, the kernel of phi is contained in G psi. Conversely, for any element belonging to G psi where H belongs to G, we have this is equal to t to the power 0 equal to I, so that this belongs to the kernel of phi. Hence, G psi is also a subset of the kernel of phi. We have thus shown that the kernel of phi is equal to G psi. Okay, now we have all the pieces that we need in order to make our conclusion, next conclusion. So what are the things we have? Our map phi has domain, which is our constructed group, and range, which is this cyclic subgroup, and the kernel is this. So by theorem 241, this quotient group is isomorphic to T, but we have shown that G itself is isomorphic to this. So not distinguishing between isomorphic groups, we can write this quotient in place of this. So this is isomorphic to this. So let us write these things. So by theorem 2, I forgot the 271, yes, not 241, 271. This is isomorphic to the cyclic group generated by T. Since G itself is isomorphic to G psi, so we have note that as a subgroup of this G psi, which is practically the which is the same as G, because we are not distinguishing between isomorphic groups, is normal. So G is normal as a subgroup of this. And what is the reason for that normality? It's because G psi appears as the kernel of the homomorphism phi. Kernels are always normal. Okay, so we are almost done. Now the only thing left for us to show is that the previous 21 order non-abelian group, that case is actually a special case of this. Now we know what is the underlying group, as well as the automorphism, all those things we know for the previous case. So we just have to show that the binary operation we have defined here reduces to the binary operation that we got in that verify exercise. Then I mean that is all we want to show, and that is all we have to show. So let's just write like this. Now we specialize the above discussion to the case where our group is this, a cyclic group of order 7, that is A is an element of order 7 and T is this map which maps the element AI to A to the power 2i, and automorphism of G of order 3. We just have to verify that the operation that we have defined on H. Recall that in the previous verify exercise our group of symbols was denoted H. H in the previous verify exercise matches with the one here. Okay. So let us see, for x to the power I, a to the power j, x to the power k, a to the power l, belonging to this. Do you see how the previous group at least how the symbols are actually what we have here. I mean, in this special case where our group is the cyclic subgroup of order 7 and phi is this automorphism, the symbols are just what we previously had, because now in place of these symbols, the G's, the group elements, are going to come from this cyclic group generated by A. So the G's themselves will be powers of A. So that's how in the previous group we got this type of symbols. So for this, using the operation we have in this exercise, we get if we just simply use what we have defined here, then it's going to be this. Where note that now in place of R we have 3, because phi is an automorphism of order 3. And now here we have something. Let's see what. In place of this, we are going to write a2 to the power k j a l. We will say why we are writing this, but let's just assume for the moment that this equals a to the power 2k times j. Then use the rules of exponent in our cyclic group. Plus L okay. Now since this is a cyclic group of order 7 and A has order 7, so in place of this plus we can write our that other plus, which gives us the remainder when this integer, this exponent is divided by 7. Now according to the notation that we used in the previous verify exercise, this plus is plus 2 and this plus according to that same notation is plus 1, where recall that plus 1 denotes the remainder when I plus k is divided by 3, and plus 2, this operation gives us the remainder when this thing is divided by 7. You go back to that exercise, you will see that. Now there are several questions, not several questions but 2 questions here. How is this a to the power j phi to the power k equal to a to the power 2k times j, and how is this equal to this? This second question almost you can understand how to answer, because 2 to the power k j plus l is congruent to 2 to the power k j plus 2l mod 7, and A has order 7. So using these congruences, and by now we have done it several times. Now this type of calculation, you will see that these two elements in our cyclic group are equal because the exponents differ by an integral multiple of 7. Now the other question, how are these two things equal? To understand that, of course, in the general case, you have to prove it. Okay, using induction or by some other means, you have to prove it. But you can see a special case. What is phi cube actually? Phi cube is applying phi 3 times. Okay, one after another. If you apply phi once, then what is the definition of phi? A 2 is multiplied with I. So you have 2I. Then you have phi square. On that, if you again apply phi once more, again another 2 will be multiplied. So a to the power 2 square times I. And finally, if you apply the outermost phi, you get 2 cube I. So if you have k number of phi's, and note that k is a non-negative integer, because that's how we have constructed the group today. K is a non-negative integer, so it makes sense to say k number of phi's. Of course, if you have k equal to 0, the meaning is something else. In that case, phi to the power k is the identity automorphism. But if k is positive, then you can say phi to the power k is k times phi. We are applying on a to the power j. So in that case, you can see that k will appear as the exponent of 2. Okay, in this power 2 to the power k. So I am not going to write these other things systematically. You can see for yourself how these two things, I mean from here, from this to this and from this to this, how these two things are justified. Okay, now you go back to the previous verify exercise and you will see that this is equal to this. That's how we have defined the binary operation there. So this general group that we have constructed today reduces to this one. So this is a more general one and the previous one is a special one. So you see that we mentioned this specifically, that even when G is abelian, this group that we construct is non-abelian. This is, in this case itself, G is abelian because it's a cyclic group of order 7. So we can always make any group a part of a larger non-abelian group, provided we get an automorphism of the original group that is not an inner automorphism, and number 2, it has finite order. Okay, so this completes this discuss exercise, and I am going to stop the video here itself. In the next part, we will solve the actual exercises that we have at the end of this section, and then of course our study will continue. So this was a long one, and now I feel somewhat light having shown all these things. Now that these things are over, we understand. See, these many things were there behind those small paragraphs that we have in the text. So anyway, so that's all for tonight. What do we have tomorrow? Tomorrow we have calculus. I'm trying to remember if I have anything else to say. Did I forget anything important? No, I think that's all. So until next time, this is me, Lucifer, from a mathematical room. Comment in the comment section below if you want. So see you next time. Have a nice night.